Here's what's going to happen now. You're going to listen to me right up to the point where you agree with me or you don't. Then either you'll find something else to do, or if I have your attention, you'll post a comment that espouses your worldview. This sounds great, except it isn't great. Because whether you agree with me or not, a huge percentage of you won't listen past the point where your personal biases are confirmed. If what I'm saying is inside your comfort zone, you'll stop listening because we see eye to eye. If my words are outside your comfort zone, you're going to stop listening because you don't want to be uncomfortable. It gets worse. The echo chambers created by our confirmation biases are filled with narratives designed to blanket us in the comfort of the information we want to hear. Objective truth is getting harder and harder for humans to uncover. So how will it ever be possible for AI to figure it out? What can we expect from natural language processing? What are the limitations of neural networks? What is the state of the art and where's it going? It's my pleasure to introduce Google AI product lead Barak Turovsky, who's here to help us dig just a little bit deeper into deep learning. Barak, take it away.
I'm Barak Turovsky, and I lead the Languages AI product team within Google AI org. I'm very excited to present the latest and greatest developments in Languages AI that will have profound impact on many industries and business cases. First of all, I wanted to kind of explain a bit what Languages AI means. On a high level, it's just much better natural language understanding, what we call NLU. And if you abstract it and oversimplify it, it's mostly consists with two big use cases. The first one is monolingual language understanding, just understanding in one language, let's say English. That means understanding text, understanding speech, in just one language. The second big bucket is translation, which is effectively bilingual language understanding language A and translating the text or speech to language B. So those are the two big series of use cases related to natural language understanding. Now, why language understanding is so important? Well, in the world of technology, our goal is to help user manage the world with technology through the power of language. And not surprisingly, language understanding is a critical component of many technology products. For example, Google Search, it's all about language understanding. There is a lot of other Google products like Gmail and YouTube, etc., where language understanding is a critical component because at the end of the day, people seek information or communicate. All this requires language understanding. Now, language understanding might sound very simple because languages, when people learn languages, it comes naturally, so to speak. You start learning a language when you're a child, and it sounds very simple. But when you look at it, and especially when you start to understand how machines who are not humans, how they can understand languages, it's actually extremely complex because our languages are hard. They have rules and exceptions to the exceptions, and rules to the exceptions. And the way we communicate could be ambiguous. For example, a sentence I'm learning Go could have multiple meanings. It could be programming language, or it could be learning a game. It could be various ways to express yourself. For example, I work for Google has more or less the same meaning as Google employs me. Language is also evolving. For example, this not even very readable slang word in Italian means I like you very much, and this is a real world. TV, TTTTB. It also could be very contextual. They were out, for example, could have multiple meanings. So that's just a series of examples to show you that if you look at the blank state, like machines start to learn language, language is extremely complex and hard. Therefore, what Languages AI is, on a high level, what it is, it's basically using deep neural networks on huge amounts of training data, and a couple of big use cases or examples of technologies, deep neural network technologies that are used on this front. One is bidirectional encoder representations from transformers. It's a very long name, and we in short call it BERT. That's basically neural network-based technique for natural language understanding pre-training, and I will expand on it because it's becomes one of the critical technologies in monolingual language understanding. And the second one is neural machine translation, or what we call NMT. That's a technique that uses deep neural networks to translate from language A to language B. So let's go a little bit deeper into each one of them. So in terms of monolingual language understanding, only recently, state-of-the-art architecture for languages AI was what was called recurrent neural networks. Recurrent neural networks process words sequentially. This works very well modeling short sequences like sentences, but they struggle with making abstract associations because in many cases, abstract associations requires to understand the context of multiple sentences, paragraphs, or even entire story. Now, in 2017, we made a leap forward with our research on transformers, models that can process, or they actually process words in parallel. And 1 year later, in 2018, we used it as a foundation for a technique we called bidirectional encoding representation from transformers, again, BERT. Now, BERT models can consider the full context of a word by looking at the words that come before and after it. Now, BERT models are also pre-trained using plain text from the web and other textual sources. On a high level, we use the same technique we use for search. We crawl the web in finding relevant text, publicly available text, and we use it for training of BERT. To do that, we actually use a process to train it that is a little bit like Mad Libs. For example, what we do is that we hide about 20% of the input words, and we train the model to guess those missing words. So for example, in this example, as you can see, we hid the words like grass and habitats and cold, ground, marble, small. Now, when we train BERT in this way, it can actually predict missing words in text. But this is generally on its own is not that useful. However, what it turns out is that when you train a model in this way on billions and billions of words of text, then this model learns an enormous amount of language understanding and word knowledge. To some extent, in similar way like human process enormous amount of information over the years and start basically forming language understanding and knowledge about the world. And this approach is much more effective at understanding language versus previous recurring neural networks approach because the model can now learn what we call general concepts and apply them rather than just memorizing facts. Let's try to use an example. In this particular case, we have a task that we do care about. For example, let's say we would like to be able to answer questions from a paragraph. Here is a question, and there is a paragraph that we can kind of extract the question from. So what we do is that we take the question and a paragraph that may contain the answer, and we want to generate the span of text. Like we want to generate specific chunks of text. In this particular case, it could be voles, raccoons, and scans. That's basically the answers to the question. And we look to generate those spans of text. We might have a few hundred thousands to million examples that were created by humans that might contain a potential answer or might not contain an answer. And now we can train a neural network to do this. This is the way that question answering system in general have been trained for a number of years. Since the question answering system and BERT are both based on deep neural network, we can actually initialize our question answering system with BERT. So we basically combine those two together. Then we can train this on our question answering. We can train this on our question answering system just as we did before. But since BERT already has such deep language understanding and word knowledge, we can now answer new questions that we've never seen before, much better than we could previously. In this particular example, BERT already learned the association between grass and the ground, and as well as things like mammals and voles. So now when he understands this world knowledge and those pretty complex associations, BERT can now learn to answer a question like this, even if it hasn't been, those words actually were not in the question answering training data. And this is a big step forward because we now effectively train with very little to no direct training data because there is some association and understanding about the world, about the language and understanding about the world. So that's pretty breakthrough technology. One additional pretty amazing technology in bilingual natural language understanding is obviously neural machine translation. And on a high level, the difference between our previous machine translations that we called machine learning 1.0 is that in each, we would take a chunk of no more of 5 words. We would break each sentence into this chunk, and we translate each chunk separately. Now, in neural machine translation, we take the entire sentence as a whole, and in the future, we might be able to take more than just one sentence. We might take entire paragraph. That allows us to better understand the context. It allows us to reorder the sentence in much better way to be able to create much better translation that also sound much more natural.
Okay, let's take a look at a couple of examples of the profound impact that neural networks has on language understanding. So the first example is from Google Search, where BERT helps better understand the subtle language nuances. For example, in this query, we have a query, can you get medicine for someone? Pharmacy. So any human would definitely understand that the intent behind this query is whether you can pick up a prescription for someone else. But prior to this change, our language understanding was not the best, and none of the results that we would show were particularly useful. We were just showing general results about how to fill the prescription. Those are not completely directly related to the query, because specifically the ask is how I can fill a prescription for someone else. With BERT, we are able to better understand the meaning of the relationship of for someone in relation to the rest of the sentence. And therefore, we can provide much more relevant result. As you can see on the right, the result is, can a patient have a friend or family member pick up a prescription? Much more useful. In this example, again from Google Search, BERT helps to better understand the intent behind your search. So here, the query is 2019 Brazil travel to USA needs a visa. So the word to and its relationship to the other word in the query are super important here to fully understand the meaning of the query. It's about a Brazilian traveling to the US and not the other way around. Previously, our algorithms would not fully understand the importance of this connection to the query, and we return results about US citizens traveling to Brazil. With BERT, however, we now can, search is able to grasp this nuance and know that the very common word to actually matters a lot here, and therefore Google Search can provide a much more relevant result for this query. Again, it sounds very, very non-trivial, even for a first or second grader, but languages are very complex to machines. And this understanding of those nuances is very critical and allows us to create a much, much better search experience. And here, as you can see at the bottom, there is a quote from Pandu Nayak, who is the VP responsible for search ranking for many, many years, more than 15 years. And he specifically said that with BERT, those changes represent the biggest leap forward in the past 5 years and one of the biggest leaps forward in the history of search. This just shows you the profound impact that we can do to create a much better search experience. Let's go to next example. This is a bilingual example related to neural machine translation. As you can see here, it shows the quality of translations across multiple languages in a previous system called phrase-based, because we, as I mentioned, we were breaking the sentence, artificially breaking the sentence into chunks, versus neural. As you can see, a lot of languages before were not very usable, and now they're jumping to good or higher, or they were good and now we're jumping, the quality is going to excellent. So in this particular case, you can see some of the languages are very excited, as for example, Indian languages like Marathi, the third from the left. It was barely usable and now it jumped to be very, very good. Obviously, a lot of languages like European languages or Arabic languages, we had a significant jump. Look at Russian, that was good and now it's excellent. Look at languages like Indonesian and others. So we are very excited about that. Was the biggest, a single launch of neural machine translation resulted in biggest jump in translation quality in the last 10 years combined. So I'm very excited about it. One additional thing to mention is that it's not only improving the quality of translation, but it also helps the translation to be much more natural, sound like much more like a human, not like a machine. In this particular example from Germany, as you can see, that in the old system, phrase-based, The phrase was translated as, "No problem can be solved from the same consciousness that they have arisen." This sentence, even though it might be translated correctly, but it takes a lot of mental load for people to actually understand what it means, because it's not a grammatically proper English. And as you can see in neural machine translation, the translation is much, much better, and much more natural. Problems can never be solved with the same way of thinking that caused them. Okay, now let's talk about what's next for languages AI. One of the most exciting developments that before, both BERT for monolingual and neural machine translation would use huge amounts of data, and now we're getting to a point that we're using humongous amounts of data, humongous AI models. So as an example, in translation, we have a new system that we recently published called Massively Multilingual Massive Machine Translation. It's a very long, fancy name. Called, in short, we call it M4. The idea here is that you take data across all languages, you build one humongous models across all languages, and let those deep neural networks basically learn from all those languages. And as you can see, you see pretty significant jump in translation quality. So on the left side, you can see languages that we call high resource languages. It means that they have a lot of training data already. And on the right side, you see the low resource languages that we don't have a lot of data. As you can see, when you move from 400 million parameters of training to 6 billion parameters of training, and then to 50 billion parameters of training, you see pretty significant jump in quality. There is a huge jump in high resource languages, meaning languages where we have significant training data already. But also we are improving significantly in low resource languages, and particularly in languages that we have not yet launched because the quality was not there. Google Translate today supports 100 languages that cover 99% of online population, but there is 7,000 languages on Earth. And with this development, we could potentially launch more languages quickly, including languages that before we could not launch. So that's it. Hopefully you enjoyed this presentation. And back to you, Shelly.